So my name is, can we reduce the volume a bit, or is it okay? At least to me, it feels like I'm shouting. Okay. So my name is Boaz Leskes. I'm part of the development team at ElasticSearch. And this talk is about, I think, my last 8 months or something like this, thinking about how to implement sequence numbers in ElasticSearch. So the first thing to talk about is, what do we mean when we say sequence numbers, and why the hell do we want to do this? So in ElasticSearch for quite a while, we've been tracking changes on the document level. So every time you index a document to ElasticSearch, we increment this version counter, if you can see the response, by 1. So if you want to know if a document has changed, you can very easily detect it, which has been the underpinning for features like optimistic locking, and we use it internally quite heavily in the replication logic when we move shards around to make sure we do not override newer version of the documents with an older version of the same documents, okay? It's been very useful, but we don't have any comparative notion when it comes to cross-document or multiple changes at one go. So as soon as you index 3 different documents concurrently, and actually that's 2 different documents, if you see, there's no way to track it, no way to find out what happens first, what happens second, what should be propagated, what should not be propagated, and these kind of things. So this is exactly what sequence numbers give you. Just very simply, kind of, assign a number to each operation and so we can order them nicely. Right? So it sounds very simple, and it is very simple. The problem starts when you actually want to design it in a distributed fashion. But before we go there, we say, okay, order is nice. It kind of feels intuitively correct to do, but why? So it turns out that when you can order your operations, you can build higher level features on top of that. For example, changes API, like other people have, where you can stream all the changes that happens to a specific index. That means you can do cross-data center replication easily. That means you can re-index, for example, to another index. That means that you can, if you can also filter that stream, which you're supposed to be able to do, you can also create another index, which is a view or a subset of a bigger index and tail on the changes that are there based on some criteria. Okay, so it's quite useful. And not only is it useful to build higher level constructions and higher level API, we can actually do cool stuff with it internally. And as an example, I chose to talk about primary replica sync. So in ElasticSearch, we sharded the index to many shards, and we note one of the copies as primary, is the leader of the pack. And then we have copies of that shard across the cluster. And those copies can contain all the documentation, all the documents and all the changes, but sometimes one of the copies goes offline. Maybe we restarted the node, maybe there was some issue. And when the copy comes back, it may be that the primary has an extra operation that needs to be synchronized to the replica that was offline for a couple of minutes. So the way we do it right now in ElasticSearch, we do a file-based sync. We basically look at the underlying files that Lucene creates for us, and those are oriented in a so-called thing called segments. And we see which one is different and copy over the files that are needed to be copied over and delete the files that should be going away. And that works really effectively, and it's doing its job, but it has kind of a problem. It's very crude and very rough. So for example, in this case, the only thing we can share is the bottom file. And all the 3 segments on top on the replica are different from the primary, and that's because the replica is a different Lucene index. So it cleans up on its own, it merges segments on its own, it flushes data on its own, so it's different. And that sync can be big, and if you're unlucky and it's a 1 gigabyte sync, it will take time. However, if we reliably can order the operations over there and have a sequence number, we can easily detect that only operation number 5 is the one that actually needs to be copied, which is much, much lighter weight than copying 10 gigabytes. Okay, so this is basically our motivation as to why to do it. So before we dive into the design, we need to understand a bit about how Elasticsearch indexes data currently. In Elasticsearch, we have our shards. So here's a notation. It's a 2 shards, 0 and 1. Each of them have a primary and a replica. Primaries are bold. And you can index in Elasticsearch to any node in the cluster. Right? It doesn't matter. The cluster will take your change and route it to the designated primary of the shard it needs to go to. In this case, node number 1 on the left side. Node number 1 will index this document or apply the change, and then replicate it to all the replicas associated with the same shard. And only once that has been done, when it got acknowledgement from the two different copies, will it respond back to the client. Okay? So we call synchronous replication. Notice how it routes to all the copies before acknowledging. And that's fine, but you also need to remember that most of the time, this will happen concurrently across many clients and many documents. Okay? And one of the beautiful things about Lucene as a search library that allows you to scale that way and consume all the resources a server has. So if a Lucene index is hit concurrently, it will scale up and consume everything. And that's an important aspect to make the most use of your server resources. And that's something we would like to keep. So let's look at what it actually implies. Here's another way of looking at the same thing. We have one primary, two replicas, and we index the first change into the primary, replicate it, and acknowledge the write. Same thing we could do with change number 2, but we want to do it concurrently, so there is also a change number 3 that comes in. And because it's distributed on different servers with those sequence, it may very well be that document number 2 got to replica number 1, or it's actually change number 2, and change number 3 got to replica number 2, when things kind of got problematic. And now we have this issue we have to deal with. And we'll see later more or less why this is tricky, but you can see a bit from here. So what do we need to do? We need to design something that's correct, right? Easy to say, harder to do. We need something that's fault tolerant as everything else in Elasticsearch, and we need to do something that supports this concurrent indexing in a good way, because that's how we get the power and the speed from Lucene. So with that in hand, I went out and with some other people and was thinking, okay, this sounds like a consistency problem. We want to replicate, we want to make sure we don't lose documents, we want to have failovers and all this beautiful stuff. Let's go out there and read what we have. And one of the popular guys at the blog these days is Raft, which is a consistency algorithm. It's very similar in nature to all the other ones in the way it works. So, but everything I'm going to say about it more or less maps to timestamp view replication and ZooKeeper's ZAB algorithm. And the way it works is as follows. Sorry, one more slide. So the key thing about Raft is it's built to be understandable. That was the key mission in the way they set up to go, which makes it very accessible. It's leader-based, so there is the notion of primary, like we have, that's easy. It's very modular, so it has a master election part and a replication part, which means we can ignore the election part, which we don't need for data replication, and only use the replication part. And it's being used, not so much for data replication, but it's still being used for data replication by Facebook's, it's called HydraBase. And if you know Algolia, it's a search engine, they also chose to implement it that way. So there are some examples out there. So how does it work? We index, here's the primary, we already indexed change number 1. And when we index change number 2, we send it over to the replica, to the both replicas. And Raft called this replicating log entries, that's the abstraction, and they do it using an RPC called appendEntries, just the terminology they use. And the interesting part is that with every change, they anchor the previous change as well. So they say, here is change number 2, and by the way, the previous change was change number 1. Which is intuitive when it's just 1 and 2, but with failures and changes and concurrency and different authors and different primaries, like if this primary got scouted away and we elect a new primary, that really helps making sure that we do not override changes, that we do not mix histories from two different things. We really say, here's the change and this is the previous change. Only append this if this is what you're at right now. So that's what we do. And as soon as a quorum of the replicas acknowledge, we can acknowledge back to the writer. Then we can do so-called commit it. Commit the change, and that's what's in bold here. So notice how the primary is bold right now, and replica number 1 is still not bold. It doesn't know it was committed yet. And replica number 2 is still busy processing whatever change number 2 is doing. Okay? And the next thing to do is actually tell the replicas that change number 2 was committed. Persisted. Right? Good so far? So that's good. But it's kind of tricky to do the same thing we did before. If another change comes in, we will again have to say t minus 1 is equal to 2. But you can see if this 2 and 3 happens together, there is some concurrency issue going on. Sorry. So there's some concurrency going on, because if you have this concurrency issue together, how do you deal with number 2 before and concurrently deal with number 2? They have to happen in order because of this markering. And that's one of the thing about Raft. It is a single-threaded replication algorithm. You cannot do it concurrently. And that's, again, that holds for timestamps, view-stamped replication, also for ZAB. All of them have this inherent single-threaded change control, which is tricky. Another part of it is if you acknowledge as soon as you got a quorum and you're unlucky and you do a read after write, right? We acknowledge it, we read, and you can unlucky and ask the replica that's still busy processing the change, you'll get an old answer. Okay, so you have this visibility issue between things you have written, got acknowledged, now you have to read them. So these are tricky aspects. And finally, if you lose your primary, now you have to do some fine-tuning to see which replica will you promote to a new primary. Because you acknowledged based on a subset of the confirmation, okay? So some of the replicas have the latest change, which is already acknowledged. Some of the replicas do not. So you need to go to all of them and figure out which shard needs to be the new primary. And this only works because we acknowledge after quorum, okay? So if we lose up to half of our set, we are guaranteed to have at least one, right? With the latest change. Make sense? So, okay, we talked about it. So what does it mean? It means the Raft is simple to understand. It's also simple to implement because of this. It does work by a quorum, which is good because if we have some shards that's slow and it fails to acknowledge indexing fast enough, the other quorum of the shards can continue indexing and keep up speed. But that comes with a price. We have this read visibility issue that we saw. You can read from a stale copy quite easily. And you can only lose up to a quorum minus 1 copies. Which sounds nice, but if you really think about the numbers, what it means is that you need at least 3 copies of everything in order to operate. Because for 2, there is no quorum. The quorum of 2 is 2. So if you always have to maintain quorum of the total set, you effectively cannot lose any shard if you have just 2 copies. Which is tricky if you store 1 petabyte of data, and now for high availability, you need another copy. Okay, it's another petabyte of data, or 1 terabyte, another terabyte of data. And now just because we chose a consensus algorithm that's based on quorum, we are forced to have 3 copies in total. Otherwise, we just cannot apply this. It's inherent to the correctness of the algorithm, which is tricky in terms of price. And finally, there are some challenges when it comes to concurrent indexing. It's not that it's not solvable, it's solvable, but it's tricky because the inherent replication algorithm itself is single-threaded by design. So that was kind of a disappointment, but then we were thinking about it, so okay, you know what? That quorum, we don't really need this, we can require indexing to all shards, as we do anyway. And we took a step back and went back to our original way of working in ElasticSearch, and it's called, actually, it is anchored in some model, and it's called master backup replication, which is also leader-based, right? That's what we do right now. We write into a primary. The difference is that you write all copies before acknowledging, and it also turns out that that's also a popular model. And most notably, it's if you see RamCloud over there, that's where Raft was designed. Okay, it's a distributed key value store where they developed Raft, and they chose to only do Raft for, in ElasticSearch time, the cluster state, the metadata of which nodes, things that do not change too frequently. Okay. So there are people are using that. So with this hat on our head, let's look at it again. We index to our primary, we replicate to both our copies, we only acknowledge where things are going back, and then this means that we can fairly easily concurrently index without violating the model, right? Because there is no ordering of these rights as far as the replication algorithm is concerned. All we need to do is index, replicate, get acknowledged from everyone, and understand and answer back. It's not part of the algorithm. So that's easy. However, when we lose are primary and we need to elect a copy, there is no clear choice here. Which one is better? There is no better, right? It's concurrently, it might be that some of it have these sessions, some of these have those changes, and you can merge them together, which is difficult. But you can also say, I'm trying to roll back some changes and make them identical that way. And the key insight here is that notice that the indexing operations that were acknowledged, which you are not allowed to roll back, are actually by definition available on all the replicas. So for those, it doesn't really matter which one you choose. But so if we choose replica, the upper one, we need to roll back on replica number 2, we need to roll back operation number 3, but that one was never acknowledged because it never went into replica number 2. And if it was on replica number 2, then we don't need to roll it back. So we have this nice primary election property. We can just choose any of our copies. All of them are good. So what does it, again, summarizing? Again, it's a simple model. You just index, replicate, collect all the answers, give an answer back. And there is no read visibility issues because as soon, when you acknowledge, you actually wrote it to all the copies, so you can read from every copy and it will be there. And here our failure tolerance is much higher. Right? We can lose all the copies by 1, and it's enough to replicate all the changes back to restore all the original copies. Because everything we acknowledge is actually on all the copies. So we're guaranteed to have on that single one. However, and that's a property, if you know ElasticSearch, you have it right now, if a shard is under pressure for whatever reason, it will slow down indexing for the entire shard group, okay? Because all they work together. It is a downside, it is a trade-off. So that from that perspective, and finally, although concurrency is kind of easy, on the other hand, is every time you have a failure, you will also have a rollback, or highly likely to have a rollback. Whereas with Raft, on consensus, you still have rollbacks, but you need multiple failures to get there. Okay, so rollbacks are more frequent. And the last point, which we're going to talk about next, is there is really no clear commit point, and that turns out to be important. Okay, so when I realized this, we realized this in the group, so okay, that's cool, it fits exactly to what we do right now, we can easily extend it, we just assign numbers, we just need to think about the semantics slightly differently, and everything is okay, until we realized, well, there is this problem. So, commit points, what do they mean? So there's again 3 shards with their histories, 1 out of 5, everything is synced, everything is fine, and then we concurrently index into it. Right, so we have operation number 1 to 5 is on all the copies, 6 made it to replica number 2, 7 made it to replica number 1, 8, again replica number 2, and 9 is a small document or small change. It was immediately applied and returned. Okay, so 9 is acknowledged, 8 is not acknowledged, 7 is not acknowledged, and 6 is not acknowledged. And then things happened and we lost our primary. So what does it mean? It means that we can roll back to a certain point, but we don't have anything in our algorithm that will tell us how far we can roll back. Where's our commit point? With Raft, it's very explicit in the algorithm. It says, okay, I got acknowledgement, I'm going to commit this, I'm going to broadcast this information. We don't have it. We need to introduce it somehow. Luckily, primary has all the information it needs to decide where's a safe commit point, right? Because it knows it processed all 1 to 5. It knows that all 1 to 5s were acknowledged by all the replicas, or at least it's easy to keep track of that information. That means that it also maintains this information that, that up to 5 is on all the shards. So it can also maintain a sort of a safe state and say, hey, all the shards, this is one I know is safe. And these shards can maintain the copy of this safety. Okay? Now, as you can see, as soon as we token this distributed machine, we broadcast the information, also immediately implies that the replicas will be lagging, right? Some of them got the latest information, some of them is not information. But that's actually not a bad thing. We can live with it. So think about, for example, a higher level saying, changes API, we want to stream changes. If we stream off replica number 1, and the tricky part is we never want to expose a change to be indexed in a different change if that change will be rolled back later. Right? That's the dangerous part here. We made a document, we replicated the document to another data center, then we, because of a local failure, the primary failed over and we need to roll back the change. That's hard. So replica number 1 can say, all the way up to 4 to where I knew, this is where I'm exposing my changes API. This is what's safe to do. If I reached up to 4, and yes, and ask me, is there more? At this point, I cannot commit to everything above 4. But a second later, when the primary actually broadcasts the increment of the safety point, then I can expose it further. Okay? So it's okay to be slightly delayed in time, as long as you catch up with that safety point. Same goes for our use case, which is the primary replica synchronization. So if I want to sync this new primary, for example, so we lost the primary and want to sync replica number 2 with replica number 1. So replica number 2 knows that up to 5 is safe. So it knows it only needs to sync the operation about 5, which is a few. But this one, it knows that everything up to here is safe, so it needs to do slightly more, but it's only by the amount of the safety point is lagging behind. It's not too much. It's a few documents, 1 second of data. It's not too much. So we got our design goal in the sense that we have a clear marker, we have a commit point. It moves ahead with time and allows to say up to here it's safe. Okay? So where do we stand? The design is pretty much fixed, as we discussed today. We're still working on the nitty-gritty details of how to store this safety point, where to put them in Lucene, how to store them in transaction, and how it all implies. And if you want to know more, then here's the issue number you can track on GitHub and ask questions. Love to have a discussion around it. Okay? So thank you.